From the beautiful studios of Way Happy, this is Mr. Meyer in 3.5, solving logarithmic equations. And finally, we get to really get into the nitty-gritty and start solving these equations and having a lot of fun. So let's go. There are 3 techniques to solving an exponential equation. The first one, now this is when the x is the exponent. First one is you could go ahead and log both sides. Usually we pick, log base 10 or natural log because our calculator has that button. So we could do that. You could convert it to a log equation and then use change of base, or you could use a shortcut. The shortcut method is the cleanest and the fastest, but not always usable. Kind of I drew an arrow over here and said, you'd have to notice on this problem that these are both 2 to some power, like 4 is 2 squared, and 32 is 2 to the 5th, right? And if you notice that, then you would rewrite this problem as 2 to the 2x minus 6 is equal to 2 to the 5x. And when you have the bases the same, then they're equal, their exponents must be the same. So therefore I can say this, and then I can subtract the 2x over. And then finally I can divide by 3 and get negative 2 as x and be like, wow, look at that, right? So that's a shortcut. If you can get the 2 bases to be the same, then you can essentially drop those bases and just solve for the exponents, but doesn't always happen. So a little heads up there. All right. Now let's talk about how I would solve these equations. And let's go ahead and figure out what we're going to do to this. So first things is, you always want to get the base and the exponent and whatever it's equal to by itself. So if there's anybody hanging around like this 3, you need to get it out of there somehow. And the quickest way to do that is divide both sides right here by 3. And I get 5 to the x minus 6 is equal to whatever 48 divided by 3 is. So I believe 16. So now I'm kind of set up in the form that I like, and I can then solve. Now, again, I can use the methods of trying to use the shortcut, but I can't make them both base 5, so that's not going to work. I could try to convert using change of base. I could try taking the logs of both sides, so it doesn't matter. Let's first convert. So the way we kind of learned in rewriting. And so the way I would rewrite this problem is the base is 5. So on my logarithm, the base will be 5. Remember that logs are always equal to the exponent, so I know it's equal to whatever the exponent is. And then this side is always the input of the log, that is this thing right there. And so we now have rewritten our problem. And we wanted to solve for x, so how easy is that? You're going to just move the x to the other side. I'm sorry, the 6 to the other side. And you are going to go ahead and have an equation like that. And you got 2 ways to do this. Change a base formula on your calculator, or just type this onto your calculator. I'll show change of base right here. Log 16 divided by log 5 using the common log. I could use natural log if I wanted. And I will get my answer that way. And I will be done. So here's my calculator. And I will tell her to do log of 16, close that, divided by log of 5. Where's that log button? Log of 5. And then I will add 6 to all of that. And the answer will be 7.7227. So x is 7.227. Now, if you have one of these fancy new calculators, you could have also typed that in the step before, right here, by going second, and alpha F2, I believe. Yep, there it is, alpha F2. Look at number 5, log base. And when you push that in, it gives you the log base. So I could just go 5, and then I could go 16, and then we know we added 6, and bammo, same answer, because the calculator knows how to do log of change of base formula. So not a big deal there. Beautiful work and very nice. Now, what about those people that said, wait, I didn't think of rewriting. I thought of logging both sides. So they had 5 to the x minus 6 equals 16. And that's more than welcome. You can log both sides. Also, you can do base 10. You can do natural log, or you could pick log base 5 or something, whatever you like. Now, just for fun, I'm going to do natural log of both sides, just to show you that it's not spooky as long as you lose the exact same log on both sides. legal in math. Good news is now I can bring the exponent out front. So we have x minus 6 natural log of 5 equals the natural log of 16. And now I can divide both sides by the natural log of 5. And last but not least, I can then, by the way, don't use your calculator just yet because I don't want you getting rounding errors. I want you to use your calculator at the very end. And so when I move the 6 over, now I will break out my calculator because I don't want those rounding errors to happen too early. And notice it's change of base formula right there. Natural log of 16 parenthesis natural log of 5. And then, oops, forgot to divide. That would be ugly. Second, insert a division, go back to the end, and add 6, and hit enter, and look at that. Same answer yet again. So no matter how you do it, as long as you don't break any rules, this should not be too spooky, but should be super fun. All right. So same kind of things. As you go through, just make sure that you solve and you take your time and you're being real careful. So again, I would like it to be base, exponent, and then the equal sign. So I'd have to move the 3 over, it looks like. So I will subtract 3 from both sides. And I will have negative 7 to the 2x equals negative 34. And I will even divide by negative 1 on this case and have 7 to the 2x equals 34. Now at that point, I do have a power is equal to a number. And so I'm therefore ready to do change of base or whichever method you like. I could log 7 both sides. I could log 10 both sides. I could natural log both sides, or I could rewrite both sides. Pick your favorite and go with it, right? So I think I will rewrite. So the base is 7. So that means log base 7. They're always equal to the exponent. The exponent was 2x. And the input to the logarithm then would be the right side of the equation, which is 34. So there is my write-up. And that I can just do on a calculator, and then I will divide it by 2. So I will be finished. And so now I'll grab my calculator, and I will type in F2, number 5. I will do 7 and 34. And then I will divide that by 2. And it says it's 0.9061. So x is 0.9061, I think, yeah. And you could always check this because you have the greatest tools ever. You could store this in x real quick if you wanted. And then you could just say 3 minus 7 to the 2x, right? And if I hit equals, my calculator says negative 31, which is what the right side says. And I go, wow, I know it's even right. I can step away and just appreciate my greatness. All right, what about this one? Subtract 2, so you have 5 times 8 to the x plus 4 equals 70, what did I do? 71. Divide by 5, gross. 8 to the x plus 4 equals 71 over 5. Now, again, I'm scared of rounding errors, even though this one would be just a 1 decimal answer. I'm scared of rounding errors, so I'm not going to do it just yet. I will rewrite this, though, as log base 8 is equal to x plus 4 of 71 over 5. So that is the rewrite. Notice the bases are the same. The log is equal to the exponent, and the input is what was on the other side of the equal sign from the power. Now I know that's set up. I will then move the 4 over by subtracting 4, so that's gone. And now virtual Sheila will answer the question as I go alpha F2 5. I have 8 of, if you want, put in the fraction, or I'll just use 71 fifths. And then on the back end, minus 4. And it is negative 27241. Negative 27241. Finished. Beautiful. And logs are way nicer than you would think. And again, I could totally check that if I wanted to. Now, sometimes log problems, you have to be a little careful because the fact is that you might have to use some of your properties. So just be warned, sometimes when you do these, you may have to do a little bit of work beforehand or not. Like on this one, if I notice the power that can come out front, that is a lot nicer on this problem because I can then move the 3 over and just have log of x equals 2. And now I can rewrite this thing. Noticing that I can't take the log of x from my calculator, But if I rewrite this, the base is 10, so the base is 10. Logs are equal to the exponent, so it's equal to the exponent. And the input of the log is what's on the other side. So all of a sudden, I notice that x must be 100. And you could plug it in and see if it's actually true. Also, on the this other example here, notice I have two natural logs, and actually I have natural logs all over the place. Sometimes it will be nicer to condense those natural logs. Like I remember if you have a log plus a log, then you could multiply those logs together. So I can do the natural log of 3x minus 2 times x minus 1. I will only have one log then, equals maybe the natural log of x squared. Now, why would I do that? Because I have a log equals a log. And so the nice part about that is if I have a natural log of this equals a natural log of this, then the highlighted yellow things must be the same because they're both being natural logged and they are equal. And so since that's true, let's just ditch the natural logs and solve this. So if we FOIL this real quick, we get 3x squared and then minus 3x minus 2x is minus 5x, and then plus 2 equals x squared. Get it all on one side. 2x squared minus 5x plus 2 equals 0. And now I can just solve that. Now I think that might actually factor. What two things multiply to 4 that add up to negative 5? That would be negative 4 and negative 1. Because they multiply to 4, they add up to negative 5. Got to divide them both by 2 because my good friends bottom up. And so I have one factor, which is x minus 2. That's the first one. The second factor, 2x minus 1. And if you want your answers, they are x equals 2 and x equals 1/2. And you jump up and down that you have some answers. Now, yes, you should always plug in your answers to make sure they make sense, because I am noticing right now something about the 1/2. The 2 I'm not so worried about, but the 1/2 I kind of am, because of the fact that what happens when we take the 1/2 and we plug it back into here. You might notice that we would have natural log of 1/2 minus 1, or the natural log of negative 1/2. And if you remember our 3-domain rules, you would remember that you can never have zeros in denominators, you can never have negatives under square roots, and you can never have the input of a log or a natural log of it all have it be 0 or negative. So this guy is actually extraneous. So that is it. All right, let me ask you a question and we'll be right back. All right, excellent work. Now let's talk about orders of magnitude, kind of a geeky topic, but what it is it's just orders of magnitude are when something is 10 times bigger than something else. So if you, and that's one order of magnitude. If it's 100 times bigger, then it's 10 to the second, which that means it's 2 orders of magnitude. If it's 1,000 times bigger, that's 3 orders of magnitude. So every power of 10 is what we call an order of magnitude. So like here in this example, how much longer is a kilometer than a meter? Well, you might know that it takes 1,000 meters to equal a kilometer. And that means that 1 kilometer, let's see, that's times 10 times 10 times 10. That is 3 orders of magnitude bigger than a meter. 3 orders of magnitude, right? So that's all how you figure it out, is just how many times would you have to multiply by 10, and that's how many orders of magnitude there are. So orders of magnitude, I could talk about a horse and a mouse. If a mouse weighs 40 grams and this guy weighs 400 kilograms, well, here's 40 grams, right? And then I got to get to 400 kilograms, so 1,000, right? How much bigger is that? How many orders of magnitude? Well, there's 40, but then there's 1 times 10, 10, 2, 3, 4. Wow, that's 4 orders of magnitude. I mean, it's a huge difference, right? Think of the difference between a horse and a mouse, and you can see 4 orders of magnitude is insane how much bigger it is. So orders of magnitude multiplying by 10. Where do they come in with Richter scale problems? When we talk about earthquakes, we talk about Richter scale. There's a nicer equation for it. But usually what we talk about is how much more severe is an earthquake. And so earthquakes are compared, when you actually calculate them, you can actually talk about their orders of magnitude. How many orders of magnitude bigger are they? And there's a quick little formula for that. you just do 10 to that power because, again, order of magnitude is 10 to whatever power. So in my example here, kind of nice, easy one, if we have an earthquake of 7.9, how does that compare to a 5.9? Well, notice if you subtract those two numbers, it's 2, so that's 10 to the second, or 100 times more powerful, or 2 orders of magnitude. If you look at the difference here, this is 2 orders of magnitude. And what is 2 orders of magnitude? That's 10 to the second, or 100 times more powerful. So think about that. A 7.9 is 100 times more powerful than a 5.9, and a 5.9 is already pretty darn powerful. All right, the last thing I want to talk about here is Newton's law of cooling. And this law just figures out how long it would take something to cool in a different type of medium, whether it be the air or the water or whatever. So it's neat to do with labs, and if we get some time, we can try to do a lab. But here we go. So I got a hard-boiled egg, and you can look at the formula right here, and if you have to pause it and write stuff down, great. But you can see all the different parts, the temperature at a given time, the temperature of the medium, so the outside, the water, the air, whatever. The original temperature is T0. There's the median again. K is a constant number that you usually have to calculate depending on what object is cooling. And so we have a hard-boiled egg, and the egg's initial temperature is 96 degrees. So boom, there's your T0. It's placed in 16 degrees Celsius water, so there is your temperature of your median. And after 4 minutes, hey, there's your time, it dropped down to 45 degrees. So that's your temperature at a given time. In fact, it's your temperature when little t is 4. So, because it was 4 minutes later. So now I have a nice little setup for the equation. With that information, I can figure out what the constant is. And once I know what the constant is, then I can actually answer this question about when will the egg be 20 degrees. So let's go ahead and do that. So I'm going to set it up as 45, because that's the temperature at 4 minutes, is equal to the medium, which was 16, plus 96 minus 16, e to the negative k times 4. And so now I'll solve this. I'll move the 16 over. That looks like 29. Looks like 29 to me equals 80 e to the negative 4k. And then I could even divide and have 29 80ths equals e to the negative 4k. Now at this point, you could put y1 and y2 and tell me where they intersect. But now that we've been dealing with logs, we might as well do that. Right? So I would natural log both sides just because of Euler's number, but you didn't have to. You could do whatever you want. So remember, now you got the left side. Don't do anything with it yet. Just, that's going to go in your calculator. But on the right side, natural log and Euler's number are inverses. So whatever goes into them is going to come out. And that would be negative 4k. So I'm going to have ln of 29 80ths equals negative 4k. And to get k by itself, I would just divide both sides by negative 4. And so now I can grab Sheila and say ln of 29 80ths divided by negative 4. And Sheila says, hey, it's 25368. So what do you want to call that? I guess we'll go 2537. So let's say K is 2537. Is that what I said? And there should be the decimal, not there. Can double check, I guess, by looking at my calculator. 2537 sounds good enough. I would rather have more decimals, but I didn't want to write them down. The more you're willing to take, the better off you're going to be. Well, now we have a formula, right? We got the K value, so we know exactly what is going down. So now I can take it into the problem. When will this thing be 20 degrees? So it'll be 20 degrees when the median again was 16. The initial temperature was 96 minus that median. E to the negative k, well, we just learned that k was negative or 0.2537, and t is time. And so now I'm going to solve this really the same way. I'm going to subtract the 16 and get 4 equals 80 e to the negative 2537t, or however many decimals you were willing to bring, divide by 80. So I have 4 80ths equals e to the negative 2537t. And now I can natural log both sides. So ln, again, I would do that because it's Euler's number. I can use a calculator. What's going to happen is these guys will be gone, and I can just divide by negative 0.2537. And that will be our time that our delicious egg is 20 degrees. So ln 4/80ths, right? Divided by, and again, holding off to do anything until my calculator, until the last step, so that no rounding errors. And again, I would much rather use that other one. I should have used answer from above, but there you got it. T is, what did it say? 11.81 minutes. So in 11.81 minutes, our delicious egg will have cooled to 20 degrees Celsius, thanks to Newton's law of cooling and our geniosity. I think that's a word. Anyway, have a great day. Stay out of trouble, and I'll see you tomorrow.